Let's talk about concentration cells. What is a concentration cell? How does it work? And why would we want to use it? So Le Chatelier's principle is back, right? We know that if we increase the reactant concentration in an equilibrium reaction, then the reaction should shift towards the product side. It should produce more product. If we increase the product concentration in equilibrium, the reaction will shift to the reactant side. It wants to shift and reestablish a new equilibrium to counteract the change in the system that we've made. We can take advantage of this in a voltaic cell, though, with regards to voltage. If I increase your reactant concentration as compared to standard conditions, I will see the voltage also increase on that cell. If I increase the product concentration, I will see the voltage decrease as compared to standard conditions. So what a concentration cell itself is a cell where both compartments have the same components. So if you're using like a zinc concentration cell, there's zinc on both sides. Copper concentration cell, there's copper on both sides. But they're at different concentrations, which is driving the cell through Le Chatelier's principle. We can see that in the pictures here. Both of these systems, this first picture here has copper at 1 molar in each system. This is at equilibrium. Nothing is changing, right? Again, at equilibrium, the individual ions are moving back and forth, of course, but from a bird's eye view, nothing is actually changing. So the cell potential here would just be the cell potential of 0. When I take the reaction, overall, anode, cathode, the cell potential would be 0. In the system here, though, I have a much more concentrated concentration of copper on this side than I do over here. And so what's going to happen is I'm going to actually see a cell potential. Why is it that direction? Why do I want a higher concentration at my cathode than my anode? Because remember, at the anode, I've got copper going from copper solid into solution as copper 2+. And at the cathode side, I've got copper 2+ being reduced to copper solid. So if I have a higher concentration at my cathode than I do at my anode, I'm going to see this happen in the reaction. Now, electrons flow from the more dilute solution to the more concentrated solution. This is the same reason I just talked about. More dilute to more concentrated because I'm going from the anode where it's being oxidized to the cathode where it's being reduced. The electrons are still flowing anode to cathode. That never changes. And the voltages here are usually small. We're not going to get a very large voltage difference when I'm doing this, but I will see an overall effect. So let's work an example. A concentration cell can be formed by connecting two half cells which contain the same electrolytes at different concentrations. Suppose a concentration cell is formed by connecting a 0.0010 molar zinc 2+ solution, zinc half cell, with a 0.1 molar zinc 2+ zinc half cell. Which half cell is the anode and which is the cathode, and what is the cell potential of this concentration cell? So at the anode, remember anode is oxidation, so zinc will be oxidized. So I will have zinc solid going to zinc 2+ plus 2 electrons. It's being oxidized, it's losing those electrons. At the cathode, that is where reduction occurs. So I will have zinc 2+ gaining 2 electrons and going to zinc solid. Now, if I look up the standard reduction potential for zinc, again, it's written as reduction. So I'm going to find it for this. I'm going to find E naught of the cell is equal to negative 0.76 volts, which means when I flip the reaction around, E naught of the cell is equal to positive 0.76 volts. When I add these two reactions together, overall I find zinc solid plus zinc 2+, giving me zinc 2+ plus zinc solid. I'm just not going to cancel them out because they're different concentrations. And my overall cell potential here will just be 0 volts, right? 0.76 volts minus 0.76 volts, overall 0. But I do have two different concentrations here. I have 0.0010 molar zinc 2+ and 0.10 molar zinc 2+. How do I know which one is which? electrons always flow anode to cathode. So I'm going to set up this reaction so that I have the species that's more concentrated at my cathode. Thinking about your two cells. Connecting them, you've got your zinc. You've got your salt bridge. All right, so you got zinc, metal. No liquid in between the beakers. In solution, zinc 2+ and zinc 2+. How do I know which one goes to which side? Again, I need to think about the fact that the electrons are going to travel from more dilute to more concentrated. So my more concentrated solution is going to be in my cathode, 0.10 molar. My more dilute concentration is going to be at my anode, 0.001 molar. But why? Can I see that from the reaction as well? It's hard to think about, but I want you to think about where these species reside in the system. The cathode is where the zinc 2+ is on the reactant side, 0.10 molar. The anode has the zinc 2+ on the product side, 0.0010 molar. If I look at it this way, it makes a lot of sense to me by Le Chatelier's principle. If I can write that so you guys can read it. Makes a lot of sense to me that the concentration is going to go this direction. I'm more concentrated on my reactant side than my product side, so I should see the system move towards the product side. And that's what I'm going to see. I'm going to see a higher voltage, or I'm going to see, because of Le Chatelier's principle, but I'm going to see, even though they're both zinc on both sides, the more concentrated solution is my cathode. That is the reactant side that has that species in it. So the electrons are still going to travel more dilute to more concentrated because it's the opposite of when you look at Le Chatelier's principle with the actual reaction. So all of this, shrink this down. Shrink this down. To specifically say, at the anode, I will have my 0.0010 molar zinc 2+ zinc half cell, and at the cathode, I will have my 0.10 molar zinc 2+ zinc half cell. Now, what is the cell potential of the concentration cell itself? Well, let's figure that out. We know that the standard cell potential is 0, right? 0 volts. So I'm using the same system, same species on both sides of the reaction. But I also know the Nernst equation. I know the Nernst equation is used when I'm under non-standard conditions. These are non-standard conditions. First of all, both species are not at 1 molar. Second of all, both species don't equal each other. So let's go ahead and use the Nernst equation. E equals E naught minus 0.0592 over N times the log of Q. As a reminder, E is the cell potential of the actual cell. E naught is the standard cell potential. So what I found from the reaction itself up here, 0.0592 is just a series of constants that are wrapped together. It's your Faraday's constant, it's your gas constant, and it's also your temperature, assuming that you are at 25 degrees C. If you're not at 25 degrees C, we'd actually have to plug the numbers into here. So there is actual numbers or variables that factor into that 0.0592. N is the number of moles of electrons transferred. And then log of Q, Q is your reaction quotient. So the concentration of the products raised to their coefficients divided by the concentration of reactants raised to their coefficients. This is equal to 0.00 volts based on my standard cell potential here, minus 0.0592 over N. If I look at these reactions, I am transferring 2 electrons, so 2 moles of electrons, times the log of Q. Now I need the product concentration over reactant. My product concentration, 0.0010 molar, divided by reactant concentration, which is 0.10 molar. and I get an overall cell potential here of 0.0592 volts. So again, it's not a big cell potential. It is a small value, but there is a difference in cell potential, even though it's the same species on both sides, on both the anode and cathode, because I'm using different concentrations. So I've created a concentration cell, small difference in potential, but taking advantage of Le Chatelier's principle.